Alright, so this chapter we are talking about gases. So we're going to be talking about just a distinct, specific phase of matter and the chemistry involved with it, the properties of gases, all of that in this chapter. So some ideas from the past will make a comeback. Stoichiometry, still going to be in play this chapter, but there's some new ideas as well. And so first, let's remind ourselves of some things about gases, or become aware of some key properties here. And so the first one is that gases are miscible, which is just a fancy way of saying they mix together. Whoops. So there's not like a solubility table we gotta look at. There's no solubility rule. It's not, is this gas soluble in that gas? They just mix. All the gases, doesn't matter what they are. If I have any two gases, they will mix together in any proportion. 1% to 99%, doesn't matter. Fully soluble within each other. And that's because they'll just occupy the same container together. And they'll mix, but they don't separate or anything like that, unless you create a special apparatus or something like a centrifuge or something to find a difference in property to separate the gases. We can also talk about how gases have high energy particles. Well, high energy is a relative term. I mean, there's higher energy things than gases, but compared to like liquid or solid, they have high energy, they're moving quickly, and they also don't really interact with each other. So they're moving around, but they're not really too concerned about what the other gas particles are doing in general. So they do interact with each other a little bit. I didn't say they don't interact with each other, I just said they barely do. That's going to be a really key thing at the end of this chapter. So for the most part, it's small enough that we can ignore it, and we will right up till we can't anymore. And then, remember that they are going to just occupy the volume and shape of whatever container you put them in. So you have to have a closed vessel. You have to have something with a screwed on lid, or an enclosed piece of glass that you sealed off in some way to contain the gas. Otherwise it just leaves. It's not like a liquid where it just settles to the bottom. It's a gas. So we're surrounded by gas right now, and it's in the shape of the Earth's atmosphere because gravity holds it down. So in a way, gravity creates a container for the air around us. Otherwise it would just go out into space. So it would leave, except gravity holds it down, just like us. I mean, I don't know if we'd want to leave Earth, but that'd be a scary jump to make. If you could take the atmosphere with you, it's all good, I suppose. But otherwise, you better be able to hold your breath for a couple light years. So, that's the key thing there. Occupies the volume and shape of the container. And this is a big one that we didn't really talk about before, but it's going to be very key for what we talk about in the rest of this video. Gases are compressible. So we can take a gas and we can squeeze down the volume it occupies. So we can push the molecules together. And that makes it so that they occupy less volume. Alright. So there's a lot of empty space between the particles, and so that allows us to push them closer together, and they still won't necessarily interact with each other because, it's like when you live out in the country and your nearest neighbor is 20 miles away. Is that really any different than if they're 15 or 10 miles away? That's still far. Alright? And that's the way it is with gases. So they, they're all hermits. They don't interact with other gases. They just sort of do their thing. And they just go until they hit an actual barrier. Bonk. They bounce off. Bonk. Bonk. They just bounce around the container. That's what they do. They don't really care what the other gas particles do. No, they just go about their business. It's like a molecular game of Pong or something. So, liquids and solids aren't very compressible, but gases are, so it's kind of a unique property of gases. And it's a good thing that liquids and solids aren't very compressible, because I don't like writing on a squishy table, and I really appreciate the fact that when I compress my brake fluid in my car by pushing down my brake pedal, it uses the, it doesn't compress it. It squishes against the brakes, makes them, the rotors grab on, or the pads grab onto the rotors. It's getting late here, I guess, and stop the car. So it's very nice. If brake fluid starts to get compressible, it's usually because it gets water in it, it gets old. You start having a little bit of a squishy brake pedal. That can be a little scary sometimes. You like, a nice firm brake pedal. You push on the brake, you start to stop. And that's because the liquid is not being compressible in the brake line. So when you push down the pedal, that mechanical force pushes the pads together on your rotor, and it slows the car and eventually stops it. And someone out there is probably thinking like, well, what about air brakes? Okay, yes. Well, that uses compressed air, and it still does the same sort of thing. It uses the pressure of the air, but yeah, the air has to be compressed a lot more to function in air brakes. You don't just use regular air. It's like you push down the pedal and you're pushing a column of air. Now you have a whole tank of compressed air that you're releasing into the line. Whole other thing. And if you didn't know what air brakes were, that's why semi-trucks always go when they stop. That's the air being let out of the brake. So it uses the compressed air. When you let off the brake, it releases the compressed air out of the line, and that's what you're hearing. So, they're compressible. They also exert pressure. I've talked about pressure a little bit now, like compressed air, things like that. So they exert pressure by pushing against the walls of a container. So this is like how a balloon stays inflated. It stays inflated because the gas particles are pushing against the wall of the balloon. It would be a soft wall, just like a balloon, right? But you inflate it, and suddenly, it's a little stronger, a little firmer than it was before. And that's because the gas particles are inside pushing against that. And so when you push against the outside of the container, in this case a balloon, the particles are going to push back. You're going to meet resistance. Might change shape, but that's what holds the balloon in the original shape, is particles pushing against the walls from the inside. And so if you haven't taken physics before, the official definition is that pressure equals force over area. And so, my finger pushing against this piece of paper right here, I'm generating a force. There's the area the size of my fingertip. Therefore, there is a pressure I am exerting on that area of the table. And there's a unit of pressure. There's so many units of pressure. But there's one in particular that really, really buys into this definition. And that's PSI, pounds per square inch. And so 1 PSI is a force of 1 pound over an area of 1 square inch. That gets you PSI. So when your tires are inflated to say 35 PSI, there's every square inch of that tire is experiencing a force of 35 pounds. So it's like you set a 35 pound weight on every single square inch of that tire. And that's the force that's, keeping your tire in a nice inflated shape, nice and round, smooth on the road. Little bit of give. You don't want, too stiff of tires. Then you feel every bump in the road. So it's a nice trade-off. You don't want them too low either, because then you lose gas mileage and you start to feel every bump in the road again. You just can't win, right? So, that's the last I'm going to talk about PSI, by the way. So, there's only 2 units of pressure in this class that we're going to talk about. There's so many more in the world, and if I find out any of you are even considering making another unit of pressure, I'm going to build a Terminator robot, and I'm going to send it back in time to kill your mom. It's the only way. It's the only way to prevent that from happening. So don't even think about it. you'd be like, oh, I'm going to create a unit of pressure and I'm going to call it the Kenny. No, Kenny, you're just not going to be born. I've had to do this 3 times now. You think I won't do it a 4th? And you can't prove it. It's not a crime to do that, by the way. You can't commit past crimes in the future. I'm pretty sure that was the whole theme of Time Cop, the 90s movie with, I want to say, Jean-Claude Van Damme. And also, if any of you have seen it, you'll know that I'm lying about the plot. But that's okay, because none of you are going to put yourselves through that movie. I think it even had a TV spin-off. I was a kid when it came out. I don't remember. Anyway, if you really don't put yourselves through that 90s TV spin-off of a Jean-Claude Van Damme movie, whew, you're digging deep into Netflix on that one. Alright. So, this is just like the physical definition. So, the gas molecules are applying a force. The area is the surface of the container, the inside of the container. They're applying a force to it that generates a pressure. Okay? Now, there are 2 units that we'll discuss in class. The first one is atmospheres. ATM for atmospheres. You might think that's for, what you go to at the bank. No. That is the shorthand for atmospheres. So, this is defined as having 1 atmosphere. The name kind of gives away where this is going to come from, by the way. Well, 1 atmosphere is the force exerted by our atmosphere. So the gas particles around us are exerting a pressure. So we're feeling it. There's a force being applied all over our body by the gas particles around us. We don't notice it because we're used to it. You would notice if it wasn't there because all kinds of terrible things would happen. And you'd be gasping for air in the process. But anyway, there's a force being exerted. And so what it is there's a column of air all the way to the edge of the atmosphere above us. All of that air is being pulled down by gravity. We are literally carrying the weight of the atmosphere on our shoulders every day. Every day when I get out of bed, that's the weight I feel, the weight of the atmosphere on my shoulders, and you do too. So, 1 atmosphere is defined by it being the pressure of the atmosphere, the average pressure of the atmosphere, because it does fluctuate with storms and weather patterns and stuff. But it's the average pressure at sea level, because as you go up a mountain, well, that's less air above you because you've kind of hiked above a bunch of it. That's why you have to, when you're in an airplane, they have to pressurize the cockpit, right? They have to, and then if they depressurize, the little mask drops down and everyone panics because no one knows how to put it on their face. I've never had to do it on a plane. Have you had to do it on a plane? Did you actually know how to do it on a plane? Were you really paying attention? You're like, yeah, I know how to put a seatbelt on. Is there anything worth reading? Boom, I'm going to use my electronic device during takeoff because I'm a rebel. Whatever it is you're doing on a plane, you're not paying attention to how to put the mask on your face. And the only thing I remember is, like, if there's a kid next to me, I got to try to put the mask on my face first while they sit there and suffer, because that's what they told me to do. That's all the little yellow thing goes there, and then, I don't know, you pull something, and then the bag may or may not inflate. I've flown too much. Alright, so, but that kid's on their own. Till I get my air, they don't get any. And that's airplane law. That's just the way it is. If I don't follow it, then the air marshal will fine me. I don't want to pay a fine. So, 1 atmosphere is the force, or I should say pressure, exerted by the atmospheric gases. So we've got a mix of nitrogen. It's like 70% nitrogen, 20% oxygen, 10% magic around us. No, just kidding. It's 10% cow farts. What is it? It's not 10% cow farts. There's some argon, some CO2, some water. Probably not so much around here. We don't have a lot of humidity in Arizona, it turns out. A little bit more where I came from. But anyway, that mixture of gases exerts the pressure on us. And at sea level, on average, oops, we get our definition for 1 atmosphere. So it's defined off our atmosphere, so what do we name it? Atmospheres. What more do you need? Alright, so that is unit number 1. Unit number 2 is millimeters of mercury. These unit names really don't leave a lot to the imagination, by the way. So Hg is the chemical symbol for mercury. Turns out the Romans did know about it, so odds are they probably all ended up with mercury poisoning because they weren't very responsible with their metals. I'll say that. They're like, hey, cool, liquid metal. I wonder what it tastes like. I feel like I could do all the math now. When in reality, they can do none of the math. Fun fact, that is a side effect of mercury poisoning. Not that you think you can do math, but that you realize that you can't like do anything. Like, if you have a serious cognitive impairment that's very sudden and onset. There have been a number of chemists who have realized they've got mercury poisoning because they couldn't do their calculations on their lab work. That's a real thing. So, naturally, it must have some other name as well. So if you ever see torrs, that's the same as a millimeter of mercury. And so this is basically just like the name describes. It's so bad. It's the force exerted by a column of mercury You'll never guess how tall the column of mercury is, by the way. That's right, 1 millimeter in height. The force exerted by a 10 millimeter column, well, that's 10 millimeters of mercury. 100 millimeters, 100 millimeters of mercury. And so, one thing that this was used for early on, we've modified the design since this time period, but you kind of have this mercury pool right off the bat. That's a bad sign. When you have a mercury pool, that's an issue. But it was a barometer. And so barometers are used to measure barometric pressure. Obviously, it's in the name, right? Now, that's the atmospheric pressure around us. So remember I said it does fluctuate. That's why atmospheres are an average. And so you can have like low pressure fronts, high pressure fronts, and there are weather patterns that go with that. Generally, when there's a big change in pressure, that means there's a storm front coming, things like that. And so one of the early ways to measure these changes in atmospheric pressure was to use mercury. So it's used to measure atmospheric pressure. And the nice thing about mercury is it's dense. And so to get a nice force, to get a weight, you don't need as much. So you can do like a column of water, but it's going to need to be, if I remember right, about 13 times taller than a column of mercury, which can be done. People have water barometers. It's a real design, but they're more of like an architectural feature and less of a useful thing. Like this will fit on a countertop. You're going to have to like build an atrium to hold a water column barometer. Alright, so here's the design. You have a tube, and it's got mercury in it, and it's in a pool, just an open pool that has mercury, and up top here is a vacuum. So there's no gas on top, just mercury below, and mercury is also in the pool here. And so what happens is the atmosphere pushes down, and then as it pushes down this pool, it's going to push it up into the vacuum, and eventually it'll reach a point where the force of the atmosphere pushing it up is going to be equal to the force of gravity pulling it back down, and that's going to give you a height of mercury. And you measure that height in millimeters from the base of the pool up to the top here, and you get millimeters of mercury. Now, 1 atmosphere is equal to 760 millimeters of mercury. So there's your conversion factor for the only 2 units of pressure I care about in this class. And I'll try not to have pascals or anything like that show up in the homework, but no promises. If you need any other conversion factors, just look them up. All right, let's just be honest about these units of pressure. It's gone too far. I mean, it's to the point where I'm threatening people with Terminator robots. Sometimes you just gotta take a shortcut. Anyway, that column height in millimeters is going to be your pressure, and so 760 millimeters. That's roughly around 2 feet in height, somewhere around 30 inches or so, 2.5 feet, I guess. And so that's not bad, right? That's something you can set on a tabletop. Now for water, you're looking at, like, if I remember right, 13 feet, 20 feet, something like that. That would be 13 to, yeah, about 20 to 30 feet. That's not going to fit on a tabletop. That's quite the large vacuumed tube you have there to hold that much water height, by the way. Not to say it can't be done, but it's going to be like as tall as a house. So you have to, I wasn't kidding, you have to build a special area to hold it. So, the other thing is, the design's been changed because it's generally not a good idea to have an open container of mercury around. So mercury poisoning is very real and very dangerous. And it's a liquid, it can evaporate, alright? And so you can inhale mercury vapor and get mercury poisoning. And so now it's generally more of a, it's like a big U, basically. And so what that lets you do is, keep a little bit, you don't have a big open pool, you got a little bit of an end here, and you can have a trap and stuff like that. And then, you just look at the difference in height. And that gives you the pressure of mercury, because like this side here would be a vacuum, and this side is open to the atmosphere. But again, you can pull some tricks so you don't have mercury evaporating everywhere. And then in here, we got our liquid mercury. Alright, so that's kind of where the unit comes from. We're going to talk about our related gases more in the next video. So that's just kind of an introduction to the properties. So they're compressible, so we can change their volume. They exert pressure, so pressure is a property, so volume and pressure. What else might there be? Oh, there's the amount of gas, and there's the temperature, and so that's the stuff we're going to talk about in the next video. So we're going to talk about a very important chapter in any law school. We're going to talk about gas laws. So that's what we're going to talk about next. It's just like bird law, only different. Okay.